All right, hello and welcome to our SANS talk on fuzzing. So my name is Steven Sims. I'm joined by Jim Shewmaker, who is a author and instructor with me at the SANS Institute. I'm the curriculum lead for offensive operations, which is the curriculum focusing on all things offensive, penetration testing, red teaming, purple teaming, exploit development, and you name it, that's what we do. So I have a lot of stuff I want to share with you in this particular talk. First though, I want to share a note, and that is I haven't been to Singapore or Thailand or Australia even, or Japan or Korea. I have not been to Asia Pacific since before COVID. I'm finally coming back next month in March to teach 660, the course on advanced pen testing, exploit writing, and ethical hacking. So I'm very, very excited to come back. I love the food in Singapore and the people in Singapore, always so friendly. And again, I can't wait to get there. So my favorite dish in Singapore is black pepper crab. Those of you who know me probably know that's true. So I'm looking forward to getting there. And after Singapore, I'm going to Bangkok to do a talk. I'll be there for a couple of days. So there are also, as you can see on the slide here, there are several conferences coming up where courses that have the topic we're talking about in this session in them. So in this session, we're talking about fuzzing for bug discovery, and both SANS Sec 660 and 760 both have fuzzing in them. And I'll talk a little bit about that as we go through in this session, but we'll be in Japan, Singapore, and a couple conferences in Australia. All right, so the talk is titled Getting Started with Fuzzing for Bug Discovery. Now, obviously, we only have an hour to do this session, so we can only cover so much. But I asked Jim to come and do this session with me. He will be doing demonstrations of showing you tools like Frida and Lighthouse and just how to set up a fuzzing harness from a modern perspective. And I'll be talking through kind of what fuzzing is, what we can get out of it, what fuzzing is not, and the limitations. So to save on time, I'm gonna not do much with the intros and just dive right in here. But thank you so much for joining, and I hope to see some of you next month in Singapore. So first off, why fuzz? This is a topic that is very important to me. It's something that I believe in very, very much. I've taught many, many classes where a student, or even not in a class, maybe I'll be on a contract doing a pen test or a red team, and someone will say, if you do a good job programming and you have a good security development lifecycle, and maybe even if you do a good static analysis and code review, there's no need to do fuzzing or dynamic analysis. I don't agree with that at all. I'm strongly against that if that's the way someone thinks, because bugs can be extremely complex, and to no fault of the developer, it's impossible to test your code under every possible circumstance under which it can run. Different patch levels, different applications installed, different versions of the operating system. That's just a few different reasons as to why it's impossible to test your code under every possible condition. Not only that, a lot of the vulnerabilities, the bug classes like use after free or type confusion, different types of integer overflows, they're really difficult to test for, especially from the perspective of source code analysis or static analysis and manual code review. A lot of the source code scanning tools are really good at identifying the low-hanging fruit. In other words, the easy stuff. Bugs that are more complex, they're just not easy to find through static analysis. So how we find them is through dynamic analysis and fuzz testing. So what is fuzzing? First off, fuzzing is when you send malformed data to a well-behaved protocol implementation or a binary application that parses different file formats. So again, a well-intended program that was written by a developer. My goal with fuzzing is to send malformed data based on the network protocol specification or the file format specification to see if I can cause it to crash, if I can get some kind of unintended response or result by sending in this malformed data. That's pretty much what fuzzing is from a high level. It's a testing technique that has been very successful over the years. It is used by all the big companies that you can think of: Google, Apple, Microsoft, even smaller ones like FireEye and beyond, Palo Alto Networks, IBM, Facebook. They all do fuzz testing. When you look at the development lifecycle, the traditional phases are you design. So you design your application and gather your requirements. So those two things can work at the same time. I need to gather the requirements from those who want me to write this application, and I need to design it. Once I'm done designing it, I go and start writing the code. That is when we can do things like secure coding, source code analysis and review. But it's not until we compile it where we get to see how the program truly behaves. My intentions can be great. They can be really good, but it's not until you compile it that we see how the program really behaves. And that is when we do fuzz testing and dynamic analysis. So again, it's a testing mechanism where we send malformed data to a well-behaved protocol implementation or a binary application that deals with different types of file formats. You might have heard the term fault injection. Sometimes that's used synonymously, where fault injection, in my experience early on, that was when we actually set a breakpoint, a software or hardware breakpoint at a specific moment in time in the process lifecycle. And then when it hits that breakpoint, we inject data to try and cause a fault. We want to see how the application behaves when it experiences an unexpected condition. That's what I think of when I hear fault injection. But again, fuzzing and fault injection, they can be used synonymously. Now, I started off this slide with why fuzz? Why do we want to do this? Well, first I said it's a standard part of the development lifecycle. It's something that we should do once we compile the code, because we don't know. Again, our intentions can be great, but we don't know how the application is going to behave until it's compiled. So that's one reason. From a different perspective, if I'm an attacker or if I'm an exploit developer, I might want to find vulnerabilities through dynamic analysis or fuzzing so that I could potentially find a 0-day. If I can find a 0-day, that is a vulnerability that's known only by me. Theoretically, no one else in the world knows about it but me. And if I can weaponize it and exploit the vulnerability, that's a very powerful position to be in. That means that anyone who uses the application where I found a vulnerability could potentially be compromised by me. So when you think of that, and I intentionally put, I'm sure some of you or all of you have already looked at the big numbers on this slide, up to $2.5 million. If we can find a exploit, or we can write an exploit that would give us remote access, remote code execution to an Android device, like a phone, or up to $2 million US. If I can write an exploit that no one else knows about to get me access to an iOS device, like an iPhone or an iPad. Now, this slide shows mobile device payouts, and this is Zerodium. Zerodium is a company that used to go by the name Vupin, and they changed their name at some point. They started off in France, and I know they opened offices in the United States and even in Singapore, where the big question is, who are your customers? If Zerodium is willing to pay so much money for exploits against these types of targets, who are their customers and what are they willing to pay? Because that's their business model, to provide 0 days to their customers who use it for whatever deeds they wish. There's no way to validate what a customer is going to use these exploits for. And there are different types of people and organizations we can sell our exploits to. So you want to be careful with that. I'm not advocating by any means for Zerodium in this example. I have nothing bad and nothing good to say. I'm just showing it as an example. The question, though, is if someone or some organization is willing to pay so much money for an exploit, what are they using it for? And who else out there is willing to buy exploits from you if you write one? Now look at the other applications here. Signal, a lot of us use that for encrypted communications. Telegram is another one. Chrome browser, Safari browser, iMessage, of course, WeChat, a bunch of different examples. There's another chart just like this one for desktop applications. So if you can write a Windows kernel exploit that allows for remote code execution with no interaction, if you're wondering what some of those acronyms mean, they're spelled out, like full chain with persistence, remote code execution, sandbox escape. What that means is I wrote an exploit or a couple of exploits the last time I sold one. So I used to sell a lot of exploits, and the buyers I would sell my exploits to were what I considered to be ethical buyers, meaning when I sell them, they're going to use it and go to the affected vendor to get it patched. So if I'm going to sell it to a person or an organization that takes my exploit and works with the affected vendor like Microsoft or Apple or Oracle and get it patched and not share it publicly, that's an ethical buyer. Now, they're not going to pay as much money for an exploit as someone who is going to potentially sell it to nation states, which makes sense. But my morals, I chose to only sell it to ethical buyers. So I got paid a lot less money. But the last exploit I sold was 3 exploits chained together. One was a information disclosure bug that allowed me to bypass ASLR. One of them was a remote code execution bug that allowed me to execute code on the target system. And the last one was a sandbox escape vulnerability and exploit. So that's what we mean when we say full chain with persistence. Enough exploits chained together to allow for ASLR bypass, remote code execution, and sandbox escape, and even privilege escalation. Even to an ethical buyer, you can get 6 figures, meaning over 100,000 US dollars for that type of chain. So I've spent a lot of time on this slide, and I think it's important because the question I asked is, why fuzz? Because it's worth a lot of money. Even if we're not talking about dollars, we're talking about the value of it to an organization. If I was Apple, which I'm not, but if I worked at Apple and I was a leader in that company, I certainly wouldn't want one of these 0 days getting out there publicly. So even the companies who are the targets of people who are writing exploits against applications and devices, they're even willing to pay a lot of money nowadays, which is interesting. So fuzzing is what we use, or one of the ways in which we are able to find bugs. But just because you find a bug doesn't mean it's something that's exploitable. Determining whether or not something's exploitable, that's another piece of the overall puzzle. We need to find a bug. We need to determine if it's exploitable. And then we need to debug it and weaponize it. And then more than likely, we need to chain this bug together or exploit together with other exploits to be able to get what I want. It used to not be that way. It used to be only a single bug could result in complete compromise of a target system. Even back in like 2014, 2015, I was writing exploits that would compromise a browser and get you remote code execution. There was no it just worked. It was beautiful. So I already answered this question, what is fuzzing? And the answer I gave was a testing mechanism where we send malformed data to well-behaved protocol implementations and applications. Makes sense. We're trying to send unexpected data or conditions to an application to see how it behaves. Now, normally, in order for me to write a fuzzer, I need to go and read the RFC, the request for comments document about the network protocol, or I need to read public documentation, such as that about a PDF document. If I want to fuzz a PDF reader or editor like Adobe or Nitro, how do I learn how the file format works? There's either documentation out there from the vendor or someone has documented it publicly and shared it. And any of those options were completely fine. But that's what fuzzing is. It even says on the slide here, humans can be fuzzers. Every single person out there has been using an application and inadvertently caused it to crash. And usually we just say, okay, it crashed. I'm going to start it back up again. Now, what did we do to cause that crash to occur is the question. That's the hard part. What series of events led up to the crash? And if I can reproduce that, then we found a bug, a reproducible bug. Then you have to have the skill set to be able to determine if it's exploitable. So continuing that, a fuzzer, a good fuzzer, should manage the entire life cycle of testing. Now, with regard to testing, we're talking about dynamic analysis. We usually provide something called a sample file. Let's say, for example, our target is a PDF editor, like Adobe Acrobat. What we would want to provide to our fuzzer is a sample file that is a PDF document, preferably one that utilizes a lot of the features. An example would be if PDF documents support JavaScript, then we'd want to include some JavaScript maybe. Maybe there's additional metadata that we can include inside the document. Well, we want to do that. So we want to provide a sample file from which it will mutate. So we want the fuzzer to be capable of generating new mutations from our sample files. We want our fuzzer to be able to start the application that we're fuzzing and monitor that application. So open the application in an automated manner, open up the malicious file, not malicious, but the malformed file or mutation, and handle that in some type of a loop. So we want a target, which is what we're fuzzing. We want sample files that it can mutate from. We want the capability to automate opening up the file, the program that we're fuzzing, and opening up the file that is the mutation and repeating that in a loop. One of the most important things with fuzzing is monitoring. If we're not monitoring and something crashes, then that doesn't do us much good. An analogy would be if there was a homicide or a murder, and there were no cameras, there were no witnesses, no one saw it. It's going to be difficult for law enforcement to determine what happened or who did it. Versus if we have cameras or witnesses, now we've got something we can work with. Same thing with fuzzing. We have to monitor the whole process so that if we detect a crash condition, we can take a snapshot and we can record that information. What type of information, you might ask? Well, maybe the context of the crash, like the registers themselves, or the disassembly where the crash occurred. Maybe the contents of the stack or the heap and other memory regions. That type of data is going to be useful. We also want to be able to, with monitoring, to maybe stop the application if it stops responding. If we send data to an application across the network and usually it responds back right away, maybe we wait 5 or 10 seconds and then say, well, the application normally responds back by now. Since it hasn't, I'm going to terminate the application and assume that we probably caused it to hang, and maybe take some of that snapshot information like the register state and the disassembly. So all of this together. Oh, another good one. If a crash occurs, the ability to take a virtual machine snapshot is always good. That's one I personally like, where if I am fuzzing like one thing I have at my home, or I used to anyway, is a browser fuzzing farm. And if I send malformed data to the browsing fuzzing farm and it caused a crash to occur, I want to take a snapshot at that moment in time so that I can go and inspect it. So later on, I can go and revert to that snapshot and I can take a look and see what everything looks like and try to determine what happened. And then we want it to be able to revert. Like, we don't want the fuzzer to stop at that point. We want the fuzzer to be able to take the snapshot and then continue where it left off. So automation is really important here. So continuing on with what is fuzzing, software developers and security researchers should all know how to do fuzzing. So hackers, or what we consider the bad hackers, the good hackers, like the ethical hackers, software developers, and everyone in between should all know how to do this. I mean, preferably not the bad guys, right? But we can't stop that. We have to acknowledge the fact that they're going to do it. So if the bad guys are doing it, we should be doing it. If we're not, we're doing a disservice. So everyone should be fuzzing. And as I mentioned, look at the company names at the bottom of the slide here. Well, the products anyway, Chrome and Windows, that's Microsoft and Google and Mozilla and Apple and Oracle, VMware, they all do fuzzing. So as a security researcher, I certainly want to do fuzzing. So fuzzing for bugs, some types of bugs are really good. Well, I should say some types of bugs are easier to find with fuzzing versus others. Other types of bugs are actually hard to find with fuzzers. And some examples are on the slide here. Like, fuzzing's good at finding buffer overflows and heap overflows and null pointer dereferences, use after free attacks, and type confusion. Those are examples of bugs that fuzzers can be really good at finding. I say can be because the fuzzer's only as good as you wrote it to be. Just because you write a fuzzer doesn't mean it's going to find these bugs. You have to know what you're doing. It takes a lot of practice. So some types of bugs are easy to find with a good fuzzer. Other types of bugs are not that easy to find with a fuzzer. Some examples from the slide: race conditions. An example of a race condition is TOC/TOU. That's time of check, time of use. But I remember a while ago, SciScan in Singapore, some people from Google Project Zero, I think it was Ginvale Coldwind and someone else, I don't think it was Tavis Ormandy, but I can't remember. They released and did a paper about how they found over 50 TOC/TOU bugs, and I believe it was with the fuzzer. So usually, though, those kind of bugs are hard to find with fuzzing, but they found a way to do so on Windows specifically. Now, let me give you an example as to why certain types of bugs are hard to find with fuzzing. Notice it says information disclosures. When we think of fuzzing and when we think of a crash condition, it's usually when our fuzzer caused a process to crash or hang. Like, that's how we know something crashed. That's how we know our fuzzer did something, because the process crashed or it stopped responding. Some bugs, though, they don't cause a crash. A perfect example is certain types of information disclosure bugs, memory leaks. There's one that I put into Gray Hat Hacking 5th edition. I'm one of the authors of that book. And it was a bug discovered by Ivan Fratrick from Google. And the bug was a use after free bug that caused a memory leak. And when you triggered the bug, what it would do is print onto the screen something that you weren't expecting to see. So let's say, for example, you were expecting the words "Hello World" to be printed in the browser window. But instead, if you trigger this information disclosure bug, it causes some weird Japanese characters to print onto the screen. Only weird because we're not expecting to see them. So instead of seeing "Hello World," we get these Japanese Unicode characters showing up. That is a perfect example of how you would detect an information disclosure bug, but it didn't cause the process to crash. So you may miss it if you're not properly monitoring it. And that's what we mean by certain types of bugs can be challenging to find with a fuzzer, because you have to design your fuzzer to specifically look for the type of output that would be indicative of a vulnerability. So that's tricky. Source assisted fuzzing, there's different types of fuzzing out there. There's randomized, there's mutation fuzzing, intelligent mutation fuzzing, static fuzzing, symbolic execution fuzzing, source code assisted fuzzing versus when you don't have the code, like black box fuzzing. So source assisted fuzzing allows us to do something called instrumentation. Instrumentation is when we compile the code and insert something called code execution marking. What that typically does is records information when a line of code is executed. So again, this is different from when you normally compile an application, and you have to have the source code. If we're doing code execution marking, we compile that application with special extra code. And that code is designed to record information when the line of code is reached. So we're basically stalking the application and recording the hits. And that allows us to do stuff like code coverage analysis, where we can determine the depth of code coverage that we get when we're fuzzing. It also allows us to generate new mutations and test cases that we can then insert. So source code assisted fuzzing is fantastic when we have the source code. So continuing on with types of fuzzing, execution fuzzing. So full program, we execute the whole program from beginning to end. Now there's a question that you could ask. If I want to fuzz a binary application like Microsoft Word or Adobe PDF Reader, is it better to open up the application, have the application open up a mutation, a mutated file, check to see whether or not a crash occurs? If a crash doesn't occur, is it better to close the whole program and kill the process, start up a whole brand new instance, and then open up the next mutation? Or is it better to keep the application open and continually open mutated files one at a time until a crash occurs or until you exhaust all the mutations? That's a tough question to answer. The answer is yes. Both ways could find bugs that the other way may not have found that bug. So I always use this example or this analogy, which is, let's say there's a mixed martial arts fight or a boxing match, and two fighters are in the ring, and one of the fighters gets a clean hit on the chin of the other fighter. Now, the person's stunned because you got him right on the chin. Now the bell rings. Had the bell not rang, the other boxer or fighter could have probably just pushed the person over and they would have been knocked out. But somehow they stayed up, but the bell saved them. Now, if this were fuzzing and we basically punched the process in the face with the mutation, but it didn't crash it, it's hanging on by a thread. It's a bad joke I always use, but it's hanging on by a thread, but it didn't cause a crash. But you kill the process and start up a new instance, and now you open up the next mutation. You just missed a bug. Versus, again, had you opened up another mutated file, it would have caused a crash. It was that succession of events that caused the crash to occur. So as I mentioned, there's mutation-based fuzzing and there's generational-based fuzzing, and we can provide a test case and have it mutate, like American Fuzzy Lop, AFL, the fuzzer. It does all kinds of different tests. It does bit flipping, it does byte flipping, it takes prior test cases and it splits them in half and concatenates them. It takes a test case and it adds random data on the end. Those are some examples of what it might do. Or you could do things manually and try to mess around with the GUI or somehow automate that. Now, down at the bottom of this slide, it's actually pretty funny. It says urandom, dev urandom, and basically pipe urandom data into an application that you want to fuzz. That surprisingly has been quite effective over the years. It seems silly, but it's essentially sending random data to a target process to see how it behaves. So yeah, it's a fuzzer. We're not going to go through all of these fuzzers, but these are some well-known examples of fuzzers out there. Sully and BooFuzz. That was originally written, Sully, by Pedram Amini, that's the author's name, to be a network-based intelligent mutation fuzzer. And then Joshua Pereda took it over and made it even better. AFL, American Fuzzy Lop, that's Mikhail Zalewski from Google. I think he works at Snapchat now, but AFL is known as one of the best fuzzers in the world. It is unfair how amazing of a job it does. Peach Fuzzer, it's been around for a long time, but it's done great things over the years. Hong Fuzz, Lib Fuzzer, there are countless fuzzers out there. And many are just proprietary fuzzers written by just a random developer or tester. Prevalence and popularity, like I said, there's lots of fuzzers out there. Most of them are research quality and unmaintained. The fuzzer that I wrote that does browser fuzzing is a perfect example of that. So many people have written fuzzers that they've never published or that they release once, but they're not maintaining it. So it requires someone to own that responsibility and really manage and baby and take care of the fuzzer. You can't just write a fuzzer and expect it to work great for years and years and years. It is a partnership. You have to love your fuzzer and you have to spend time developing your fuzzer. Now, it's good for automation once you get it working, but you always have to go and check up on your fuzzer and make sure it's doing what it's supposed to be doing. A lot of times, university research at colleges is where fuzzers come from. And there'll be an academic paper that comes along with it, but then it just dies. Like, it goes unloved. The person who wrote it or people who wrote it graduate and go get careers. But great research comes out of universities. And like it says in that bottom bullet, fuzzing is part art. You have to be creative. It's part math and science. You have to be smart and talented and a developer to some degree. And a big part of it is that end one. It's luck. A lot of it's just dumb luck or understanding something about the target and taking chances. One thing I like to do that I always point out, I take crash results from places like Google Project Zero. Google Project Zero publishes, we caused a crash to occur in Edge browser. And here is the trigger JavaScript code that caused it to crash. I will take that as a seed file and then create mutations based off that seed file. Because I'm a believer that if there was a crash in an area, there's a good chance there's ever similar conditions close by. And it's proven to be correct for me time and time again. Dynamo Rio, I'm going to finish up here pretty quickly. It's a fantastic tool to do instrumentation. And Jim is going to show you an example of these types of tools I'm talking about right now. One of the things Dynamo Rio does is it records the hits. And by hits, I mean, when we reach a block of code, it records the memory address. So I talked previously about source code assisted fuzzing. What if we don't have the source code? Dynamo Rio is an example of a framework and a set of tools that we can use to stalk an application while we're fuzzing it to see what kind of code coverage depth we get by recording the blocks of code within a function within an application. We record all of that information, and then we can export those results into a disassembler like IDA Pro or Ghidra, and we can color code our path, our trajectory through an application, which is amazing. So WinAFL, for example, the Windows port of the American Fuzzy Lot, is built upon Dynamo Rio. Another great tool is Frida. It's a fantastic tool that allows you to do things like hooking. And when I mentioned before fault injection, I think of tools like Frida, where we can take a closed source application that we don't know anything about it, and we can instrument it to the best of our abilities, and we can identify function entry points, block entry points, and we can insert code at various points in time. It's a great way to instrument and fuzz or work with your fuzzer on closed source applications. So now I probably took up more time than I should have. I wanted to be about a half an hour. I'm 40 minutes, so I'm going to stop talking now. I'm going to pass over control to Jim Shewmaker, but hopefully I set up the stage and you've got a good understanding as to what fuzzing is in case you weren't aware of it previously. Jim, off to you.
Thank you, Steve. Let me share my screen. I'm actually going to demonstrate AFL fuzzing, having some issues with Frida crashing in a VM. So we'll still show you the better of the choice. If you have the source code available, you definitely would like to use source code assisted fuzzing. So we'll switch to that, and once I can share my screen. I think you need to unshare.
Are you able to share?
Is it sharing yet? You can't see my VM?
Nope, not yet.
I might have to reconnect to Zoom. I'm getting warning security dialogues.
Okay, if you want to do that real quickly, go ahead. I'll just keep talking.
Be right back.
All right. All right, while Jim is doing that, let me just put this back up here again. Cool. While Jim's doing that, I'll just continue with my example real quickly. He's on a Mac, and Mac sometimes has a lot of big problems with sharing screens and such, so we'll let him join back in. But going back to what I was covering, I love fuzzing. If you can't tell that already, I don't know what else to say, but it's just, I've had so much luck with it, and it's made me a ton of money, which is always great. And I've had some really happy customers. But going back to the example where I used trigger files from Google Project Zero and Ivan Fratrick, my belief, my philosophy there is that, and I use this example a lot, if I was walking in a park or I was running on a trail And while I was running or walking, I found a gold coin on the ground. I was lucky enough to find a gold coin. I would assume that, well, one, I'm really lucky, and two, that there's probably more gold in the area. That I'm going to go home and get a shovel. I'm going to come back and I'm going to dig all around in that area to see if there's more gold. Because again, my belief is that there's probably more good stuff in the area, and that's the same thing with fuzzing. All right, Jim is back, so let's let you try again here.
All right, sorry about that. Security settings get in the way, happens all the time.
Looks good.
As I was saying earlier, Steve definitely mentioned that the AFL source code assisted fuzzing is preferred if the source code is available. So we'll be looking at an example of that. But the other choice, something like using Frida and the trace tools from Dynamo Rio are also quite good. We'll just be looking at AFL here. We are going to take advantage of using a Docker container so that it has all the necessary libraries isolated in a way that makes it easier to rerun. So I'm going to rerun it. Our target program is an IP decapsulation program. The source code's available on GitHub, and we have a Docker container ready to test this with. I'm just starting the container. I need to transfer in that one input file. As Steve said, you want a good input file that exercises the program, not too extreme, but something that does have a way to demonstrate the full features of the program. So we've got a sample packet capture, which is an input file that this program uses. I'm going to copy that in. First, I need to use my container ID. I'm going to copy that file in to the Docker container that's running now. I'm going to make an input and output directory as well. And I'm going to copy it into that directory. All right, so now from inside the container, I can explore the program. Normally, you might try to read the source code and you might see potential dangerous functions being called. But one of those beautiful things about fuzzing that Steve mentioned is some of those things can be hard to find with subtle errors. So we're going to fuzz it after we explore it slightly. So let's go ahead and continue. I will. A quick look at the program, just a little simple command usage comes up. We can give it a pcap input file, and we can also say where we're going to save it. So a quite simple operation. We can just run it against a file and see what it's going to do. So, for example, we could try to run this file against that and give it as an input. And just normal behavior, it processes the file. We don't really notice any errors. It is a normal, happy packet capture file. It's a packet capture that has a sample of doing IPv6 encapsulated in an IPv4 header, IPv4 packet. So there's no crash. We didn't try to fuzz it yet. We just simply tried to open a normal input file. So now what we can do is we can try to set up AFL to add the additional markings that Steve mentioned so that it can better shortcut some of the input decisions, how to mutate, how to test different things. So we'll go ahead and start the fuzzer using the input directory. We'll give it an output directory. This @ sign represents the name of the program that AFL fuzz will actually evaluate. So this will be replaced when it actually runs. And this time we'll send the output to dev null. We don't care about the actual results. We're just looking to see if it can cause any crashes. Oops. Speaking too much and looked away from the screen. So what we're looking for is we're looking for some unique crashes. If we actually can detect a couple of unique crashes, once we have a few, we might want to investigate those, and then we'll have something worth investigating. And if we don't have anything, we'll need to go back and start over, maybe change a different input file, maybe do something a little more interesting. But as I said, this may take a while. We're not going to wait too long, but we're looking for unique crashes. If we didn't get one, then maybe we have made a mistake with our command. I'm not getting anything yet. Double checking that we have this correctly. You have the input file in the right place. Now I have the order of those operations correct. We should get a little bit better results. There's input and output for AFL, and there's also input and output for the source decap. This time, I'm able to get at least one unique crash. I'll wait till I get another one. Should be happening within a minute. And then we have something that's worth investigating. As Steve was mentioning, that the AFL tool is very good about taking a sample and modifying it in smart ways so that it can find bit flips, byte flips, and so on. Now we have two unique crashes, as the display tells us in the upper right here. Let's go ahead and dig a little deeper. Let's look and see what we can do with those crashes. First of all, we can look at that out directory where it saves information about the crashes. We can see the command line, the crashes themselves. There's a lot of valuable information there. Looking at the crashes, you can see two test cases. We don't know too much except for the input file and where it is. These are actual packet capture files. We could open them with a packet analysis tool, try to decide what crash may have caused it, or we can take a more interactive approach. Instead of passive packet analysis, we can go in and try to use a debugger. So I think we'll use the debugger. We'll look at it and see if we can get some clues. First of all, the real advantage to source code assisted fuzzing is that we can look at the source code of what would be part of the vulnerable conditions. So I'm going to recompile this target program with source code debugging information. Depending upon the application, of course, you may have different changes you need to make. So this is going to recompile the IP decap program, not just for AFL compatibility, but more importantly, to keep some debugging symbols and debugging information available in the program, making it easier to see where things crash. Clean from the previous build, make it clean, and rebuild the IPD cap. And now we can actually use the newly compiled version of the program with one of those test cases. Here, I'm going to go ahead and run it with not all of the inputs and not AFL. AFL already created the crash test case. What I'm going to do is look at what was generated from AFL, which is in the crashes directory. And I'm just going to use an asterisk instead of typing out the full command. It will actually use the asterisk to expand the file name. And I don't care about the output again. And this is expected. It was supposed to cause a crash. It says memcopy SSE2 unaligned. Inside of here, somehow, we have a crash. So we can do a couple of things. One of the more useful options is just typing in backtrace. It's going to show us the functions that were called to get us to this point. Most notably, here we can see what is prefaced with a number 2. Well, we can see that there was in the handle packets. If we want to go a little closer, see what would have caused it right immediately before the function that contained the crash, we see something a little more controllable. We see in, we see out, and we see this is in IPD cap, and we see that it's line 573. So if I go pull up that source code file, IPD cap, C, and I go down to the 573rd line, you can see that there's a call to memcopy, and it copies the payload destination, payload source, and a length. And this, with that input, there's must be a size miscalculation to actually cause a flaw with this memcopy call. At this point now, we could take advantage of some of the tracing features and find out how to get to this point. Maybe we use IDA Pro's proximity view to find out how to get to this function. Or we can further analyze the input we used, resulting from the AFL crash. Then we can develop it to an exploit at that point. It really, as Steve mentioned, it almost seems unfair to use this tool because it just makes finding the crashes so easy. And that's all I wanted to show.
Yeah, thanks, Jim. And yeah, it's interesting because you saw that input size of 10, and it says the length is whatever that length was minus 2 times the struct of an Ethernet address, which is 6 bytes for an Ethernet address, right? 6 times 8, 48. Yeah. So that's 12 bytes minus the size of a VLAN tag length. So that's 10 minus 12 minus some other value. You're in a negative territory now. Memcopy expects a positive integer or an unsigned integer. So if you pass it F 4 or whatever it would end up, that's over 2.9 billion bytes that it's trying to use for the length. So clearly you are going to cause a problem at that point. And what you'd want to do is figure out how you can massage that input so that you can get it to be not a negative value, but a large enough positive value to maybe you overwrite something like a virtual pointer or something else meaningful. But I'm going to go ahead and put my screen back up here real quick, because we are at the point where at the end of the webcast, and hopefully you enjoyed it. Again, I will be in Singapore with Jim. He will be doing a little bit of teaching. I'll be doing teaching for 660 in Singapore next month in March, but we've also got 760 runs coming up in Japan as well as Australia. And if there are any questions, we're at the end right now, but we're happy to hang out for a couple minutes and answer something you might want to ask on fuzzing. But otherwise, have a great week, and we will hopefully see you soon. But we'll keep an eye out for those questions for the next couple minutes.
Thanks, everybody.
I don't see any yet, but I'm going to hope something comes in. Only takes one person to start with a question, and then you know how it works. All of a sudden, other people start asking questions. Cool. Well, I still don't see anything coming. Uh-oh, where's one? Where is a good place to start learning fuzzing? That's a good question. Off the top of my head, I can't think of a great website that's like, hey, this is the place where you want to go. Let me think here. Jim, if you got something, please throw it out there. There's a tool, though. I'm going to type it in the main chat. There's a tool I mentioned in 660 called TAOF. It's called the Art of Fuzzing. It is a simple mutation fuzzer with a built-in proxy. That's a great place to start because you don't have to be a developer. You don't have to know anything about the protocol you're fuzzing, but it will capture traffic like FTP or SSH or Telnet or whatever. And then you can select fields that you want to fuzz, and it will start mutating through it and cause potential crashes. Like that's a good new, like simple tool to start using. All right, some others. How much time on average do you spend determining if a bug is exploitable? That's a tough question, Takahiro. How much time on average do you spend to determine if a bug is exploitable? Now that one comes a lot from experience, like understanding different bug classes out there and knowing what to look for in processor registers or in memory. If you've ever like done a simple buffer overflow before, maybe you sent a bunch of A's in and you saw 41414141 in the registers, so you know that's your data. When you're dealing with something like, say, use after free, those types of things don't show up in the registers. So what you have to know at that point is if it is a use after free bug in a browser or in a word processing document, then there should be a register that holds a pointer to an object where if you're using a proper tool like page heap with G flags in Visual Studio, so again, that's page heap. What page heap does is it creates, so every memory allocation gets its own page in memory, and it inserts a bunch of metadata in there, debugging metadata, so that if you cause a crash to occur and it's something like a use after free or a type confusion, you would see that a register points to an object, and if you were to dump that object, you would see some of the very specific metadata that you're looking for, indicating if that object is free or if it's in use. So I know that's a quite technical answer, but again, my point is that your familiarity with different bug classes is what's going to determine how you know if it's something you should continue to investigate, because not all crashes are exploitable bugs. So it's that familiarity with the different bug classes and knowing what to expect in the processor registers or in memory at the moment in time when a crash occurs that would allow you to determine if it's exploitable. So see how that's a tough question to answer, but it's a great question. Different methodology for fuzzing different types of applications. Absolutely. Like I said, for example, if you're expecting to potentially see a memory leak or an information disclosure bug, it might not crash the actual process or application. So you have to know, and you have to tell your fuzzer what types of conditions you're expecting to see if it did trigger that type of a bug. And yeah, different types of applications. If it's an application written in Rust versus C++, there's a lot of bug classes that aren't applicable with Rust because it does safe memory management. So absolutely, depending on the programming language and what it is you're fuzzing, there's different techniques you would use for sure. It's funny, a bunch of questions popping up now. You mentioned skill set to identify a bug, then weaponize it. Could you plot out a trajectory to that skill set, what it would be? Example, where to start, what areas to expand knowledge in. Yeah, that's another tough one to answer, Ryan. I'm reading through it again. Identify a bug, weaponize it. You can plot a trajectory, skill B. Yeah. What I would recommend, and I might not be answering your question, but what I would recommend is looking at different known vulnerabilities and known exploits and known bugs out there, like going to exploitdb.com and downloading a vulnerable application, because they have those vulnerable applications there for you to download, and looking at the relative exploit code and then writing a fuzzer to trigger the bug. So even though you know where the bug is, you kind of cheated, writing a fuzzer to trigger the bug so that you see what the crash looks like inside the debugger. And then you're like, oh, so when I trigger this kind of bug, I know it's triggered because the RDI register shows some certain data. Or I know if I turn on G flags and page heap, that when I trigger this type of bug, that the register points to these values. Again, it's not a great answer, but it's a lot of trial and error and getting used to dealing with known bugs, how to crash them, what type of fuzzing causes the crash to occur, and what it looks like in memory once the crash does occur, and just doing it again and again and again. So again, not a great answer, but it's the best I got in this short amount of time. But we are at the end. We're a few minutes late here. I love that you guys ask questions. I appreciate it. I'm up on Twitter. I'll type my handle in the main chat. It's at Steven Sims, and I do a weekly stream on YouTube called the Off by One Security channel, Off by One Security, where we talk about stuff like this. And I'll give Jim a minute to say anything he wants to, but we're about at the end of our time here, and I appreciate you guys for coming. Jim, any final words? You're muted.
Not really a whole lot more to add to what Steve said, except for I would say that, you know, when to know when to stop, and that experience, it is a difficult thing to answer. Sometimes I would just like to add, I tend to focus on that until I get something else distracting that looks like lower hanging fruit. But I tend to spend too much time trying to chase down things that aren't truly exploitable until I get something else shinier, I guess. That's all I'd like to add.
Jim does that. He likes to go into the weeds and chase things. So no, thanks, Jim, for coming on, and thank you all for attending, and hopefully we'll see you in a class or at least online. Thank you.